Hi, our group is the Infinities. My name's Rhea, and our group is me, Bia, Jeremy, and Stom, and we'll be presenting on how math and physics are intertwined. As an overview and to motivate this presentation, I just want to cover the ideas we'll be discussing. Generally speaking, we're going to cover the motivation for math and the history of physics. Along the way, we'll talk about how their histories merge and what can you do with them right now. Mathematics is between discovery and creation. There are arguments for and against each side. In line with that, the application of some mathematical ideas is normally thought of secondary. Math is unlike most sciences, as it can stay fully abstract. So how does that affect its applicability in physics? Mathematics is extremely effective for physics. Eugene Wigner, a Nobel Prize-winning physicist, described it as unreasonably effective. There's been multiple instances where an abstract idea created purely to follow some train of thought that was just interesting turned out to have some purpose in physics years later. For example, algebraic group theory created Lie groups to model continuous symmetry of differential equations in the 19th century. In the 20th century, they were used to help categorize particles in particle physics. And this happens consistently. Look at imaginary numbers, which were created and defined rigorously to have an answer to the square root of a negative number in the 14th century. Now they help model fluid dynamics in the 20th century. Chaos theory was discussed as early as Aristotle and is now found to be perfectly represented by a double pendulum. Note the force diagrams below and the graphs to the sides highlight the pathway of the double pendulum. Math is still that abstract. Some of the biggest research right now are really interesting questions but may not be the most useful things in the world. The sum of 3 cubes is a question that describes itself. How can we form numbers in the form of a to the third plus b to the third plus c to the third? Just recently, there's been a breakthrough in the way to represent 42. The Collat's conjecture are 2 arbitrary equations, which applied over and over again seem to make any number 1. The 2 equations are if the number is even, half it, and if the number is odd, multiply it by 3 and add 1. Noticeably, not very applicable to today's world. Kirigami is being mathematically studied just as origami was. Kirigami is the idea of paper cutting, whereas origami is paper folding. And maybe this is stuff that will applies to physics of the future. But now let's talk about how physics came about to even use this.
Physics essentially comes from the observation of nature and is a collection of rules that we use to understand the way matter interacts. To give a timeline of when math and physics came to be, the earliest evidence of written mathematics is from 3000 BC, and mathematics first became an organized science around 500 to 400 BC. So, a bit of time. And in the realm of physics, we started to see mentionings of Aristotelian physics around 400 to 300 BC with Aristotle, and physics eventually graduated into its own concrete study with Galileo and Isaac Newton in around 15th to 17th centuries. Our word physics that we use today with the little s originates from late 15th century and denotes the natural science in general, but especially the Aristotelian system of physics. Going back, we can see that the plural of obsolete physical thing was suggested by Latin physica, and Greek physica, natural things, came from physis, nature. In his lifetime around 384 to 322 BC, Aristotle founded the system known as Aristotelian physics, and said that physical phenomena leads to the discovery of natural laws. Our beloved Aristotle wrote in his first work, which refers to the study of physics, that was intended to establish general principles of change that govern all natural bodies. It's not in the slide, but physics in Greek should sound something like physik-kroasis, because physics was different from physic, which meant natural things. It was his first attempt at trying to give a name to the study. I want to reiterate the meaning of physics. I was reading a book called The Disordered Cosmos, where it describes physics as the human process of developing a mathematical understanding of the universe. It said in quotes that physics is not the universe. It's one very human attempt to get to its innards. I want us to keep this in mind while going into the second slide. Aristotle promoted the concept that observation of physical phenomena could ultimately lead to the discovery of the natural laws that were governing them. Key concepts of Aristotelian physics included the structuring of the cosmos into concentric spheres, with the Earth at the center and celestial spheres around it. He said some weird stuff, like our planet was made from 4 elements, earth, air, fire, and water, as well as a 5th unchangeable celestial element called aether. Objects made of elements had natural motions, he said. Those of earth and water tended to fall, air and fire, they rose, and elements are subject to change and decay. The speed of such motion depends on their weight and the density of the medium. Aristotle also argued that a vacuum could not exist, as speeds would become infinite. About 100 years later, Archimedes tore apart Aristotle and his metaphysics, pointing out that it was impossible to separate mathematics and nature, and Archimedes proved it by converting mathematical theories into practical inventions. He developed many things such as the law of buoyancy, also known as Archimedes' principle. He founded hydrostatics and statics. In mathematics, Archimedes used the method of exhaustion to calculate the area under an arc of a parabola with the summation of an infinite series, and gave a remarkably accurate approximation of pi. As one of the first to apply mathematics to physical phenomena, Archimedes' achievements in this area include a proof of the principle of the lever, the widespread use of the concept of center of gravity, and the enunciation of the law of buoyancy. If Archimedes were alive and studying at CME today, he'd make some pretty awesome final projects, as he's credited with designing innovative machines such as the screw pump, compound pulleys, and defensive war machines to protect his native Syracuse from invasions. He also developed the principles of equilibrium states and centers of gravity. It's these ideas especially that would influence the well-known modern scholars Galileo and Newton.
In the following two parts, Stom and I will introduce two examples from physics to show you that math is really the foundation for physics. I will introduce a simple example from Physics 1, and Storm will touch upon a little bit of modern physics and astrophysics to show the continuity of mathematics in the way of supporting physics from ancient history to modern days. I believe all of you are quite familiar with these three laws, Newton's laws of motions, because they are the basis of classical mechanics. It overthrows the view of famous philosopher Aristotle's view that a body was in its natural state when it was at rest. And for the body to move in a straight line at a constant speed, an external agent was needed continually to propel it. Otherwise, it would stop moving. And the law also sums up Galileo's view on motions. All three laws in English can also be expressed as equations for people to understand. This will significantly lower or even eliminate the barrier of language differences between scientists from different parts of the world. So the first law states that a body continues in its state of rest or in uniform motion in a straight line, unless acted upon by a force. So in mathematics, the net force exerted on an object is zero, is equivalent to the derivative of velocity with respect to time, which means the acceleration of the object is zero. In this case, the object will continue to move in a straight line with uniform velocity. This is a highly hypothesized model since there will always be a quantity of frictional force acting on the object by nature. So the object will eventually come into a complete stop. As a result, it is only a matter of time. The second law states that a body acted upon by a force moves in such a manner that the time rate of change of momentum equals the force. This is the most famous equation of the three. The derived form from the equation, which is the net force that exerted on the object equals to the mass times the acceleration of the object, is often used in high school physics and Physics 1 courses. As you can see from the definition equation from the left-hand side of the PowerPoint, which is in the form of momentum, we could use the derivation from the middle of the PowerPoint to deduce our familiar part of the equation. At last, the third law is relatively simple. It basically means that if you exert a force to the other people, they will exert the same amount of force on you, but obviously in the opposite direction. The usage of the law extends to more complex physics models, such as energy, Lagrangian equations, and other analysis under the domain of classical mechanics.
Oh, so Jeremy has already introduced one example of Newton's laws in mathematical form, and then I'll introduce one more example on how the combination of math and physics can do amazing things, such as astronomy. And as we all know, time and space are the most basic components of the universe, but Newton's gravitational theory ruled the physical field for hundreds of years, and people wasn't able to really see the connections between the gravity and the time-space directly in that theory, until Einstein deduced out this equation below, combining the mathematical tools with his genius physical intuitions. Also around that time, many other famous physicists like Bohr, Schrödinger made many other amazing discoveries in other fields of physics by doing the same thing, using math to help exploring new physical rules and using physics to explore the world. So let's dig a little bit deeper into the equation itself. So what does this equation qualitatively tells us? Basically, what it is stating is that the distribution and density of energy and momentum in space determines the extent of time-space curvature, which is the essence of gravity. For example, in this picture, the hole is the place where time and space is much more bent than the other areas. And that also indicates a much larger gravity and a much denser energy distribution there, according to the formula. But we can also state that in plain language, so why do we need an equation? Of course, because we cannot get the quantitative result without using math. Math acts as the most basic tool we use in science to solve questions. And here in this equation, we use something called the tensor to get the exact extent of time-space curvature, which uses a matrix to express the physical space and distribution of matters in that space. Of course, physical thoughts and ideas are the most key part in deducing this equation. A bunch of matrices won't solve any gravitational problems in the real world. So that's why combining the two subjects are so important in cosmology and astrophysics. So that's basically all of our presentation, and thank you all for listening. And here are our sources.